derivative. Negative r sine t, right? And then r cosine t. What's the magnitude of that? Square root of r squared sine squared t plus r squared cosine squared t. What can you factor out of both of these? R squared, and then you get the 1 to come out. Square root of r squared, r. You would just get r, wouldn't you? dt. What's the antiderivative of r? With respect to t. Yeah, right. RT. Plugging in 0 and theta. I know I'm working through this fast. R goes in for t, r theta. And you plug in 0, you get nothing. So that would mean that S is what? R theta. Does anyone remember that formula from pre-cal? Or physics? The length of this arc is the radius times the angle, as long as your angle's in radians. Where does that formula come from? Right there. We just did it, right? We just generated that formula. All right, that's awesome. See, I got to stop doing that stuff because that's not part of the plan today. All right. All right, now if we go to three-dimensional space, it's the same formula. Nothing changes. So you don't need to read through that. It's the same condition. You can't cross over itself. You recognize this function. What does that draw? Right? We called it a spiral last time. It's not. It's more like a spring. Spiral, you think of it like growing, getting bigger as you go out. This is like a spring. It's the outside of a can, going up the outside of a can, or like the helix thing. So find the arc length of this three-dimensional vector curve from the point 1, 0, 0 to negative 1, 0, pi. So there's a couple of things I need if I'm going to use this formula. I need to know limits of integration, right? A and B. Am I given A and B? Explicitly, is it right there in front of you? No. Can you tell me what A and B are? A is what I plug in to get this point. B is what I plug in to get this point. So what would I have to plug into this vector function to get this point? It's another one of those obvious ones. It's given away by the third component. T is 0, right? If T is 0, check it in here. Cosine of 0, 1. Sine of 0, 0, 0. So you get 0, right? So T is 0 down here. That's what would start us off at that point. What would end us here? T is pi, right? So check it again. You could plug pi into these. You should get these 3. So we stop at pi. And now I need the magnitude of the derivative, don't I? Magnitude of derivative? Let's do that right here. What is the derivative of this vector function? Negative sine t. It's kind of a, that's funny. I said this on, I was making the solutions, the homework problems for 10.8. I finished them today. And then when I was doing it, I was sounding like a broken record because almost every single time I was doing a problem, it always had sine and cosine in it. And that's the way that the author saves you. You know, when you do that square root, it turns into something nice. If it didn't, can you imagine integrating something that would be really like crazy? Right? Then you'd have to pull out your old Cal 2 stuff. What is this last one? 1? Now the length. Square root sine squared t plus cosine squared t plus 1. Which is what? Square root of 2. So we're just integrating root 2 with respect to t. And if you do that, you should get pi times root 2. I'm not going to do it. That's how long that curve is. I might have the picture of it also. Let's see. Yeah, there's the picture. So you'll notice, well, I've got a bunch of stuff in the way here. I have the computer telling me what t is and what the arc length is. So I'm measuring that red piece until I get to, where were we going? Pi? We're only going to pi, so pi is like 3.14 something. I just put it in here. Pi. Okay, so someone on their calculator, what's pi times root 2? Just verify for me. What's pi times root 2? 4.4? Really? Oh, it didn't do. Oh, it didn't take the pi. Okay. Why didn't it take pi? That's weird. Oh, I didn't enable dynamics. That's why. There we go. There we go. 3.14, 4.44. As long as you can integrate the magnitude of the derivative, you can find the length of any curve, as long as you have the vector function that draws it. Can I share that problem? Okay. Daniel, right? Daniel? Sent me something that he found online where it was they were measuring the length of a DNA strand, a chromosome. One chromosome. It was we think it was a problem, right? You think it was a problem from a math class? It's hard to say, right?
I just typed in because when you did the double helix,
yeah,
it didn't exactly look like DNA. I was like, I know there's a function out there for the DNA.
Okay.
I just typed the DNA vector helix.
Okay. Yeah, so he was able to find the vector function for that models the chromosome, right? And in this problem, they were measuring the length of it. And I guess it was a realistic problem, like those were actual measurements, because what did it turn out to be, like 3 inches?
2 meters.
2 meters or something like that. So if you were able to take that strand and unwrap it and pull it, it would be 2 meters long. So like 2 of these. It was a single chromosome? Really? Huh? Interesting. But it was cool. All right. Why don't you take a minute? Guthrie, 210? Let's just do this once. Let's find the arc length. Let's just take the derivative, find its magnitude. We won't do any of the integration. All right? What's the derivative of this guy right here? Three t to the 1/2.
1/2.
Derivative, not anti. Right? -2 sine 2t. That's your derivative of cosine 2t. Then derivative of sine 2t is 2 cosine 2t. All right, there's your derivative. And then the magnitude. Square root 9t, right? Square this, you get 4 sine squared 2t. And then square this one, you get another 4 cosine squared 2t. What can you factor out of these two? A 4. And then that becomes a 1, right? The fact that they both have 2t in them, that doesn't matter. So you have just a 4 out here, right? So what does this turn into? Square root of 9t plus 4. And that's what you would have to integrate. And that would integrate pretty straightforward. You could do a u substitution if you want just basic, let 9t plus 4 be u, and then integrate up. But see, it's a little more complicated than what we've been getting. We've been getting constants, haven't we? That one's a little more involved, but definitely not crazy. You think you could take it the rest of the way? Yeah. All right, that brings us to the last topic in this section, which is called curvature. It's a way of measuring, okay, the curvature of a vector function is a number which represents how quickly a curve changes direction at a given point. And there are two formulas for calculating the curvature. We use this K here for curvature. It's, you recognize this? Capital T was the what? Unit tangent vector. It's the unit tangent vector. Okay, it's the derivative of the unit tangent vector divided by the derivative of the, sorry, magnitude of that, divided by the derivative of the position.
You said how fast it does what now? Curvature?
How fast the curve is curving. How fast it's turning, right? That's one formula. Sometimes this is easy to compute, sometimes it's very difficult to compute. There's the alternative formula. It brings in the second derivative of the position function. So, and you have to do a cross product and a magnitude. Does anyone have the book with them? You do? Just want to look at something on that. Let me make sure it's not a typo. You're good. Curvature. Yeah, okay. All right, that's it, two formulas. Now, I want to show you like a picture of what's going on. I'll do that as soon as, well, there. Look at this one. I'm gonna press play here. Well, there's no play. I don't have a play button. There it is. So I want you to notice if you're moving along this curve, which is a unit circle, right? Then the curvature, we're measuring at any single point its tendency to want to turn, right? Does it make sense that on a circle, at every point you should have the same tendency to turn, the same curvature? Well, if we compute the curvature, look at what it is. It's 1. It's always 1, no matter where I am. So the computer is actually changing t and computing curvature, and every single time it does it, it gets 1. Let's actually verify that ourselves by finding the curvature of this. The answer should be 1. So how do you want to do it? You want to use the first formula or the second one? Second one? The second one requires a cross product, doesn't it? Did you see it had a cross product? And couldn't we only do cross products on vectors in three-dimensional space? Yes? There's a workaround. If you want, let's do the workaround. I like the workaround. This is R of t, right? What I'm going to do is I'm going to extend R of t into three-dimensional space. Watch. Now R of t is in 3D, isn't it? Does that draw the same curve? That's still drawing me a circle in the xy plane. The z coordinate is always 0. So it's like on the xy plane. Same circle. It's just now we've moved off the sheet of paper and we're out there in three-dimensional space. Now we can do it. So do I have to show you the formula or do you all have that down? Okay. All right. I could write it down, but you could also print out the notes that are provided for you or bring a laptop. So what is it? The curvature is the magnitude of the cross product between the first and second derivatives of the position function divided by the magnitude of the first derivative of the position function cubed. That's it. So we need the first and second derivatives, don't we? Let's do the first derivative. First derivative is, what is the first derivative? Negative sine t, cosine t, 0. What's the second derivative? Negative cosine t, negative sine t, 0 again. Do I understand this, my first and second derivatives? What am I supposed to do with these now? Cross product. Now cross product is where we had to cover up the I and do that little thing and cover up the J and do that little thing. That's what I'm about to do. And I wrote them down vertically intentionally so that I could actually do this cross product. But I'm going to put the answer over here. What is R prime T crossed with R double prime T? So we've got cover up these and then go ahead. Cosine here and then that's what, 0? And then 0? Yes. This is a vector, isn't it? 0. And then I get 0 again when I do that?
Yep.
Damn, nice. Last one. Sine squared t minus negative cosine squared t, which is really sine squared t plus cosine squared t, which is 1. What is the magnitude of this? So what's the magnitude of this? Well, it's the magnitude of that, which is just 1. Square root of all those squared is just 1. And then I need to divide it by the magnitude. So that's the numerator is 1. The denominator is this cubed. So we have to take the magnitude of this. But what's the magnitude of this? It's 1. So 1 over 1 is 1. So the curvature is 1. That's boring, right? But you get the idea of how you would use that formula. And not only that, if you have a two-dimensional vector function, how you can extend it into three-dimensional so that you can get the curvature using the second formula. Here's an example of a vector function that does not have constant curvature. Like the circle, it was obvious, right? If you're on the circle, you've got that same curvature the whole time. This is a spiral, and it's a tighter spiral in the center, and it kind of gets wider as you get bigger. So does it make sense that the curvature should be large in the center and get smaller as you move out? So a larger curvature is like, how fast it's turning. So look in here. I think I can slow it down. Or I'll just pause it, move it back to the beginning in here. Right there at the very beginning, look at the curvature at here at time 0.01. The curvature is what? Almost 2,000. But as I move out, notice that number's gotten smaller already. Now look at that, not much further away. At 0.12, the curvature is 23. And then as I move out further and further and further, now my curvature, look, at 1.2, the curvature is 0.05. So it's kind of like, if you've ever been on one of those carnival rides, where you put you in there and they start whipping you around, curvature is like how much feeling you have of, getting, what do they call that? Force that wants to pull you in, and isn't there the force that wants to pull you in, force that wants to pull you out? Centrifugal and centripetal. There's two different ones, right? I've heard there's really only one, but okay, we're not going to get into that. Find the curvature. What formula do you like? I like the one we just used, but let's try the other one, okay? Let's just try the other one. The other one was the derivative of the unit tangent vector magnitude over the derivative of the position vector magnitude, right? All right, so I'm going to need to find the derivative. What's the derivative here? Ooh, nice. 1, 1, 2t. I need the magnitude of this. What's the magnitude of this? Square root 1 plus 1 plus 4t squared. What is capital T of t? What's capital T of t? Not this, but what's capital T of t from last class? It's this divided by its own magnitude, right? And this right here is a number, isn't it? And so I just divide each of these components by this. So watch, I get 1 divided by this root 2 plus 4t squared. And then I have 1 divided by root 2 plus 4t squared again. And then finally 2t divided by root 2 plus 4t squared. Ooh. That's my unit tangent vector, isn't it? But I don't want that. I want its derivative's length. Do you want to take derivative of that? That's going to suck. Do you agree? And even after I'm done taking derivative, then I have to find the length, which is the square root of each of those components squared. That's really going to suck, isn't it? Which is why I'm going to lean towards the other formula now. And that's what would indicate to you to lean towards the other formula also, is when that looks really bad. Now, like I said, sometimes this is easier. Sometimes, you know, you get here and you take the derivative and you get numbers and everything's just super clean. But when that doesn't happen, the other formula is probably more useful. So on the other formula, do we need these two? Yes, but instead of this, we use the second derivative also, right? So let me get my second derivative in here. Is my second derivative nice? Oh yeah, 0, 0, 2. And I'm supposed to cross these two together, right? I'm using that formula again. What would r prime t crossed with r double prime t be? Let's see. I'm doing these two crossed, right? So cover this up. What do we have there? 2. Cover the middle up. 2, 0, but then subtract, so -2. And finally, cover up these two, 0. What am I supposed to do with that in the formula? Find its magnitude. So what's the magnitude of this? Square root of 8, right? 4 plus 4. So
Shouldn't it just be 2, 2, 0? 2 minus 0
2, what?
for your components,
Where?
for your j?
Covered up these. Should be 0, 0. Is that what you're talking about? For j, the middle one? Oh, the middle one. That's 2, and then that's 0. But because j, remember, you always subtract. We good? We're not done, right? So the curvature, I'll just cheat and I'll use this formula. The curvature is this. That's it, right? We know this is what? Root 8 over, and then the derivative Is this the derivative right here?
Yes.
The magnitude derivative, right? Cubed. This cubed. So it would just be square root of 2 plus 4t squared cubed. That's it. So do you see for this curve, the curvature actually depends on t, right? Depends on where you are on the curve. As t gets bigger, what's going to happen to this curvature? As t gets bigger, the bottom gets bigger, the curvature gets smaller. And that's what was happening in that spiral. This is that spiral, by the way. So as time went on, the curvature got smaller. When time was very small, the curvature got bigger. All right, I hope that illustrates the importance, I guess, of knowing when to use which one. When you do your homework on curvature, just realize both of them are there. And I have an updated homework assignment. This is the updated homework assignment. What I've changed in here is I think I took out number 12, I added number 7, and then 13 through 16, I think I had only asked you to compute capital T in the previous homework assignment. And I said, but if you read the instructions, it asks you to calculate capital N. And I haven't told you what that is, and I'm not going to tell you what that is. I want you to go in there and read the book. There's a formula for this. It's not that much crazier, but I want you to on your own, read through the book and figure out what this is, and then try and see if you can determine what the geometric relationship is between these two vectors. This is the unit tangent vector. This is the unit normal vector. Geometrically, how are they connected? So see if you can figure that out on your own, reading through the book. And I think that's it. What do you think? I still have 10 minutes. Sorry, I still have 10 minutes. I don't want you to feel like you're not getting your money's worth here, all right? 10 minutes is something I'll beg for later. I'm going to introduce you to the next section without getting into too much detail. It's very visual. So visual, in fact, that can somebody, can you kill a few lights? Just, yeah, that's good. I don't know how that's going to come out on camera, but let's try it. Okay, we're moving into a new chapter now. Okay, a new chapter in the book, chapter 11. There are 13 chapters in this book, right? Our plan is to cover 10, 11, 12, and 13. Finish the book. That's my plan. We'll get to the last page and be done. Close the book, all right? So 11.1, functions of several variables. Okay, we have seen already that anytime we have an equation that has x, y, and z in it in three-dimensional space, we could get like these quadratic surfaces, right? These ellipsoids and spheres and hyperboloids, all these different things, right? But if you can take that equation and you can solve it for one of the variables, like z, so you get z on one side of the equation, then essentially you've got, let me blow this up. If you solve for z, then the other side of the equation just has x's and y's, then we can say that z is basically a function of x and y. Instead of like we used to say in college algebra that y is some function of x, right? When we had something like y equals x squared plus 2x plus 1. So you give me an x, I spit out a y, right? Here, if I get z by itself and the other side is x's and y's, then you have to give me an x and a y, and I can spit out a z. Understand? Remember, one input, one output is what we needed to have a function, right? One input, one output. With this sort of notation in mind, this notation, z is some function of x comma y, the input, since I have to give you an x and a y to determine z, the input can be looked at as being a point living in two-dimensional space. The output is a single number, and it can be looked at as being just a number on a number line. So that means you need 2 dimensions for the input, 1 dimension for the output, so we will be able to visualize this picture in 3-dimensional space. I'm jumping ahead here. So this is a picture. This is a picture of what I'm talking about. You have the input, right? So you have to pick an x and a y somewhere, and it's 2-dimensional space. And then it spits out a number over here, right? That's our z. But I can visualize all of that in 3-dimensional space. If I look at the ground as being the input, and the z coming up, the height of the point as being the output. So as I move around, if I pick different points, do y'all see that I'm moving around the top of that surface up there? Do y'all see it up there? Okay. So for every point in the domain, we have an output up here. Here is an example, our first example, of a function of 2 variables, x and y. Here it is. See? You give me some x's, you give me some y's, you can spit out a number, can't you? First question, what's f of 2, 1? That means replace x with 2 and y with 1. And it matters, the order matters here, right? 2 is x, y is 1. So what would this be? Square root of 2 plus 1 plus 1 over 2 minus 3, right? Which is root 4 over negative 1, so negative 2, right? So we plug in a point, it spits out a number. Let's try another one. F of 0, 0. What do you get? On top you get root 1, don't you? Which is just 1. On the bottom you get negative 3. And so this is just negative 1/3. It's pretty clean, pretty straightforward so far. All right. What about this one? Square root of negative 4 plus 1 plus 1 over negative 4 minus 3. Uh-oh. This is square root of negative 2 over negative 7, isn't it? And you can't do the square root of negative 2. Not unless you're willing to come in and bring imaginary numbers in, which we're not. So that means that this point cannot be plugged in, right? Which means there is some restriction on my domain. The question is now, what is the domain? And I have enough time to show us. What is the domain? So let's talk about it. What are we afraid will happen with this function? What are some things? Just look at it up there algebraically. What are some things that you want to avoid? What's that? Sorry. What negative 3? What? Positive 3? What do y'all think?
If x is positive 3, you can't.
Okay, we don't want x to be 3, right? We don't want x to be 3. So we have this so far. This cannot be true, right? That bottom cannot be 0, which means that x cannot be equal to 3. Agreed? That's one thing. What's the other thing we don't want? Or you can say it the other way. What do we want? We don't want a negative under the square root, right? So I've got to make sure that x plus y plus 1 is never negative. So greater than or equal to 0. That's what I want, right? What the hell is that? Oh, this is a linear inequality in 2 variables. I actually went over this when I subbed that class the other day for Math 1324, which is Business Math 1. This is Just move everything over, right? And you get this. If I were to say that's an equal sign, if I were, then that's a line, isn't it? But if I say this, then it's no longer a line. What is it? It's a shaded portion of the plane. So let me try in the last 3 minutes. I'm going to have enough time to get some idea of what's going on here. Okay, first of all, this is my domain, right? Remember we just said the domain is in two-dimensional space. I cannot have x equal 3, right? Remember, this is x, this is y. So what does x not being equal to 3 mean? What's that? S. That's right. At 3 here on the x-axis, of course I can't have that point, but I can't have any x values of 3. So this entire vertical line is pulled out of any possibility. Yeah? Then it's okay to have this line, right? If I make that an equals, it's okay to have that. Let's graph that. It would have a y-intercept of -1 and a slope. So it would be like this. Y-intercept of -1. It would go here and have a slope of -1. So it would go something like this. And it would, of course, not go through there. And then go this way. So that line is okay to have, yes? Now, which side of the line is also okay to have? It's either going to be the top side or the bottom side. How do you check? You can just plug in any point and test it. So let's just test this point right here. That point's good because it's the origin. Does 0, 0 work in this inequality? Yes. Yes. 0, 0, 1 is bigger than 0. That works. That means everything on that side of the line works. This is the domain, everyone. It's actually part of two-dimensional space. And the only way to really see it is to graph it. So that means that if I go now and I graph this function and I look on the ground, that stuff is not, this stuff right here, above that is the only place I have picture. I'm going to show you the graph and then you may go. I forgot to pass out the sign-in sheet, but that's all right because I gave back your test today. Here's the graph. Look, this is the graph of that function, everyone. That's the surface. It's weird, right? See it? Isn't that weird looking? It's doing some weird stuff. Watch this. I'm going to look at it from the top. Straight down. Do y'all see it? If I look at it from the top down, it's this. What I just drew. It's that line at 3 taken out. It's this line and everything that way. Okay. We pick up where we left off next week. Your mini exam is due on Monday, right? Yes. So, y'all have a good weekend. Can someone hit the lights, please? Thank you.